equations.
Okay, thank you very much for having me here. I mean, great fun. Here are my collaborators in this marathon. Zakaria, Bianca, Bonicewicz, and I should also mention Ektapanwar, which is not this going to start doing this stuff also now. And from Malta, we have Mirko Consilio and Tonia Polaro. So nice team. And yeah, I mean, maybe at some point you have a problem with this entanglement or whatever. This is just a random thing. So, like, you could ask this question in general, you could ask with big partitions into 1 versus 2 cubics, you could ask for genuine three-part entanglement. So, and probably okay, so what does it mean entangled? Entangled means that it doesn't belong to the class of separable states, and separable states is a convex set. I mean, so surely there is distance, some distance between this set and the point we are studying, so the state. So of course we can somehow measure it, so of course the measures satisfy discriminants, monotonicity, continuity, normalization, activity, and computability. So we have to know a way how to compute this stuff if you really want to discuss any amount of whatever. And here's small cartoon. So to know the robustness, you need to know the boundary of the separable state at least in 2 points. So the state you are mixing, because obviously it doesn't make sense to take the state from interior, and the state at the other boundary, which is like at which you look at entanglement. So like this is very complicated to calculate, but here we take a different approach. We take a Schmidt measure. Of course, this was not at all a new idea. It was proposed by Peter and Brax in 1999, and it basically an distance, right? So you take trace of square of the difference of 2 matrices. This is invariant on the unitary, so there's no problem. But we want to take this distance, the minimum of this distance over all separable states. Okay, but then a year later there was a paper by Ozawa, very nice paper. So he took 2 operations. One is just conserving the ground state, the other is the completely amplitude operation, and he took 2 states. So the second qubit, as you can see, is just a flag into orthogonal states, and the first one initially is in the maximum mixed state. And if you apply this operation, you of course end up in the pure state, because that's amplitude damping. So the distance between these 2 states actually increases under this operation. And that kind of Hilbert-Schmidt distance as a candidate for a good entanglement quantifier, because Witte Platz paper has about 100 citations, this one about 200. So they didn't do much of a career in these last 20 years. However, this doesn't bother us, because I mean, we know that we expect that LOCC will not create entanglement, right? And the other thing is that we do not study a distance between 2 fixed states, but between a set and a state. So this proof of Ozawa doesn't include the maximalization. So yeah, let's go. It turns out there's a very efficient algorithm to estimate this distance. So you take any point P, any state rho for us, because we're talking about states, so I think we're talking about states. So any state that you want to check, it's in the set, and any state inside this set. This should be 2, sorry. Okay, so what do? You take some state rho 2 from the boundary. I will discuss that in a minute. Then you minimize the distance between the line connecting your point inside the set and your point from the boundary with respect to, with the P0 probably outside. If it's inside, then very rapidly you can reconstruct this state exactly. So each time you make a better and better approximation of the closest separable state with respect to Hilbert-Schmidt measure, and the computational cost is just solving quadratic question, right? So this is very efficient because you don't diagonalize your matrices, you don't do any numerical solving, everything is analytical. So every step is very efficient, and the only limitation is the size of your matrices. And there has to be some hard condition, because otherwise we will never get to the end. Okay, so this was already used in 2 different cases by Miguel, Thomas, and Stephen for finding new Bell inequalities and Stevens inequalities, and by Ottolina and Shang for classifying LOCC class, equivalence classes, but they never studied the difference. So, okay, so in details, I mean, first of all, like we don't optimize the state after we take it at random, rho 2. Just if it goes in the wrong direction, we just discard it and take a new one that turns out to be very efficient computationally. But if it goes in the right direction, we apply local unitaries to make it a bit better. Okay, and the other thing is how to generate the state. Of course, we don't know how to generate any separable state, because that's the name of the game. We don't know how to generate any product state, but we know how to generate pure product states with uniform with respect to Haar methods, and this was given by Rzyszkowski and Sommers. And like conveniently, you can also use flat distribution to generate that for some reason. So like, okay, example 1 was the simplest for many for different dimensions that I would skip, but example 2 was of course the GHZ n-cubic GHZ state, and we were able to find the analytical form of the closed separable state. You can check that it's closed separable state, so as a reference state it should be of course reconstructed because it's separable. Or very well reconstructed as a starting point for the next iteration of the algorithm. I mean, then you won't get any correction. So that's how we check. And the distance, the square distance behavior tends to 1/2 very fast, which is not the most we have seen in this regime. Okay, so there's a lot of info you get from this algorithm. So like, first of all, you don't reach a number which is close to 0. That already tells you something. Then you can study you can anticipate the closest separable state, but that works obviously in a very few cases. Then there's this effect that if you study state deep in the interior of separable states, then the convergence is very fast and goes in a few minutes down to numerical precision. Then, okay, studying the spectrum, and then you can study the convergence to the limit of your distance, and tell about in a minute. And then, of course, you get a free entanglement witness, which is really cool, and that was noticed by Fernando first in 2005. So if you have the closest state with respect to Hilbert-Schmidt distance, this constitutes a line which is perpendicular to hyperplane, separating set from your entangled state. So that's a natural witness, but we don't have it. We only have the approximation. So what happens is that you can have, I mean, you have to check whether your approximation gives you a witness by maximizing over all separable states. And yeah, I mean, for very weakly entangled state, that would not work as you would hope, but still, I mean, in many cases, we get the witness with very high precision. So that's, and here I wrote the mean value of the witness. Okay, so one application that we did was studying UPP bound entangled state. So you have all these plaquettes, and like you take projections onto these plaquettes, but not to the symmetric state within this plaquette, and then you take projector onto symmetric state with respect to the whole Hilbert space, which is phi c, and then the complement of this hyperspace of this Hilbert space is your is proportional to your bound entangled state, because you cannot produce any more orthogonal product states, so the rest must be entangled, which is nice because I mean it's boring to study states with negativity. So, but on the other hand, we know that it's the same. So that was the first exercise. Here in the green, you see the estimated distance, square distance that we have. In black, we have the witness distance, and in the blue, you have the last found distance by the algorithm with that many corrections. And in the red, you see a previous witness. So most of the time we got a bit better. And what else can I say? Aha, this is grouped by the size of the medium chart, right? Because I mean you have to categorize the consumption. If there's any logic in this, I don't know, but whatever. So like the other information that is very useful is the decay. And this decay, well, I mean, basically, d squared would decay to the limit like 1 over n, where n is the number of steps. So we are using that, and we get very nice approximate straight lines on these graphs, and like the quality of these estimations of the order of 10 to minus 5 sometimes. So that's quite precise. Okay, this will skip. Okay, and this was used in some projects, and Mirko's role and Tom is supposed to propose to challenge this algorithm against variational algorithm, and we were trying to think if that could be done on quantum computers. So not really, but we kind of made it hybrid. So the idea is that you just take an arbitrary new state of 3 qubits, and then you try to fit the parameters to, these were the states that we considered, so these are maximally entangled X, 3-qubit X states, and yeah, these are different optimizers put in the same graph. So the Gilbert is almost at the bottom for almost the cases, only one algorithm, one or two algorithms was as good as this one. I mean, the difference weren't very good, but it turns out that there's not much point trying to do anything else. This is a very efficient algorithm. Okay, so this I will skip. And yeah, one thing that I tried. Okay, so Beatrix Hilmeyer wrote a paper where she was classifying so-called magic singlet states, which are just mixture of two bad states. And like she had some procedures. So she had, of course, she studied, of course, negativity, then she studied some analytical criteria, then she numerically optimized weaknesses, which she claimed that 2 weeks on Vienna supercomputer, and then in the last step she did machine learning. So these are her families of states. These are the vectors of eigenvalues of in the bell basis. And yeah, I decided to check it. And the last step was the state in blue were classified by machine learning techniques as potentially entangled. So if it's magenta, then the algorithm claims that it's entangled. So here you can see that well, not machine learning, sorry, artificial intelligence, different algorithm. So it's tried very much to be creative, but like it didn't have the physical content. So I thought that this was a good idea that to check. So the Sonic test was to study family A, and I found that there was almost no entanglement except no GPT entanglement except for this corner here. So that was known by Beatrix, but then the family B was different. So family 2 was a bit messy in the results, but still you get the idea. And you can, I mean, these plots are in very high agreement, especially these estimates are in high agreement with what Beatrix had after her numerical approximation, but not after machine learning techniques. And what else? Here, I mean, I did some final study on the BP, so you can see which red region you don't expect any entanglement really. Here you have zoom of PPT part of family D3, and actually this is the weakness graph, weakness distance graph, and here you can see that some points not detected by her methods are indeed confirmed to be entangled. Okay, here's a small slide how the estimate behaves. So you can see that unfortunately it's quite unpredictable, because I mean sometimes it can go to zero for very few steps, but then it stabilizes. But I cannot say after how many steps. That really depends on the state. I mean, from one state there's very different. I mean, yeah, for one state it's different than for another, so that's unpredictable. So okay, one step per, I mean, one project that it turned out to be useful was going back to the magnetic susceptibility, which was an entanglement weakness that we showed in 2005, and it was demonstrated experimentally for very high, very broad range of temperatures. And you take the second derivative of the partition function with respect to the magnetic field, and that gives you the variance of magnetization. So I decided I'd take a small, using, okay, I take a small, Heisenberg chain because it's isotropic, and I study the thermal state. And I found out that the leading correlations in the low temperature states are of the 6th order. So I thought that we thought that it would be nice to take the higher order magnetic susceptibility and change them in such a way that in the end you extract higher order correlations by taking the higher power of the magnetization that you receive. But yeah, this is the new entanglement criterion, thermal entanglement criterion. So here you can see the dependence of critical temperature where the entanglement is detected against the number of particles, and here are the limits. So there's a small improvement, but that's fine. Okay, my time is up, huh? Okay. Sorry.
Okay.
Questions?
Well, thanks for the talk. So, questions, please. Hey. I wanted just to comment because you were mentioning that the Ozawa, the argument of Ozawa didn't. I mean, he showed that the Hilbert-Schmidt distance does not fulfill. Does not fulfill contractility or data processing, but this doesn't imply. I mean, it's correct that this doesn't imply that the minimal Hilbert-Schmidt distance to separable states.
Yeah.
I mean, it doesn't answer the question whether this can increase under LOC or not. But in 2015, I had a paper with actually proving that the minimal distance is not monophonic under LOCC. This is a paper with Remigiusz, Ogusiak, Maciek Demianowicz, and Maciek Lewenstein. So
okay, I mean, what was the operation that you used, maybe?
Oh, well, effectively, you can just locally discard particles, and this would.
Okay. I mean, yes, I'm aware of that problem, but from the recent consideration of the problem of multipartite entanglement. Again, I would point out the solution of that. So, I mean, adding and removing particle is more fundamental problem that you will get there.
Oh, I mean, this is just a comment because I think for your study doesn't really matter whether it increases under LOC or not. Thanks.
Okay, further questions?
Thank you very much.
If not, I have a question.
Okay.
So,
yeah,
you said for very weak entangled states, you may be able to detect them. This is due to numerical precision or because the algorithm is not.
Okay, I mean, in theory, you can run the algorithm for very, very long and detect everything, like if you do it for months. But first of all, the frequency of the subsequent correction, of course, drops down. And the second thing is that, I mean, as I said, I mean, you don't know which way from your current row one is actually the actual closed separable state. So your weakness is, I shut down the presentation, I cannot go back in slides. Anyhow, I mean, your weakness is tilted. So you care about the weakness, of course. So the problem is that it will take ridiculously long time, maybe months of computing to fix that weakness that, you know, it just hits the boundary between the states. So, I mean, it's not a numerical problem, it's a problem that you need just too high precision and too many steps. It's not a problem of numerical precision as having as many digits as you do.
Okay, but if you would have an infinite amount of time and numerical precision, your
Then-
algorithm would converge?
Then I claim, yeah, it converges always, yes.
Okay, thanks. Okay, any other questions? Not, then our next speaker is Ray, and he will talk about the asymptotic and analytical theorem or something.
Can you share your screen? Yeah. Oh.
Can you keep it like yours?
Yep.
And you can open it.